something 500 meters across is so low, physics gets very weird. You could not stand on Itokawa if you were to go to Itokawa. Any slight twitch of your muscles, you would fling yourself in your spacesuit off the asteroid and out into space. And you might not come back down again, because that's how low the escape velocity is. And it's like all the other asteroids I've shown you, and all but the couple largest ones, it's very obviously not round. So we've got what look like roughly two ellipsoidal pieces sitting on each other, but they don't slump down, even though they are unconsolidated gravel and other sizes of rubble, because there is less pressure in the middle there than there is if you stick your hand and put it on the table underneath your hand. That is how little pressure is on the inside of these objects. So it doesn't take much strength for them to hold themselves in quite varied shapes against gravity. And we also get other weird effects that we don't normally think about for geology, stuff like electrostatic charge. So Christine Hartzell at the University of Maryland, many others have worked on this. Gravity here is so low, you have solar wind coming in, depositing protons, electrons. You can charge up actually fairly sizable grains of material and then levitate them. And they can migrate around the surface and resettle elsewhere. We also, particularly importantly for the near-Earth objects, have to worry about effects of radiation pressure. So sunlight has, like all light, has energy and momentum. It doesn't have any mass, but it has energy and momentum. So if you shine sunlight on the surface, there's a very weak pressure being exerted. Again, not something we normally worry about for geology, but when the gravity is tens of thousands of times less than we have on Earth, it becomes significant. This has been studied by astronomers actually for quite a long while now. About a century ago, Ivan Ostarovich Yarkovsky first figured this out on a theoretical basis. It wasn't observed to actually happen for decades afterwards. But it's called the Yarkovsky effect. So you have an asteroid out in space, we have the sun, it's spinning. Everything is spinning to some degree. Some asteroids spin more than others. You have the afternoon side of the asteroid. That is the spot where it's the hottest. So there's the most infrared light coming off the asteroid, that part. On the night side over here, it's relatively cold. Less infrared coming off the surface. Infrared heat is also, photons are also light. They carry momentum. It's not balanced, so there's more pressure being exerted this way due to there being more photons going off in the opposite direction. Newton's third law, there's an equal and opposite reaction. More photons go out, the asteroid gets pushed the other way. The key point about the Yarkovsky effect is that it depends on the direction the asteroid is spinning. So we have the asteroid spinning. If it's spinning one way, it gets pushed forward in its orbit, and its orbit eventually expands. If it's spinning the other way, retrograde rotation, it gets pushed backwards along its orbit, and the orbit eventually shrinks. So there's this complicated interaction between the asteroid's size, shape, and density, which determine how much the Yarkovsky acceleration is, and the direction that it's spinning, which determines the direction of that push. This was first detected in terms of actual application. Early satellite work, there was a project called ECHO. They launched a large balloon that was illuminized on the outside, inflated in orbit, and you could bounce radio signals off the balloon. The balloon kept moving in ways that they had not expected, because radiation pressure was pushing it around. And thus the Yarkovsky effect has been observed. Now, the balloon has very light weight. It's very thinly spread gas inside. Rubble pile asteroid, density is typically at least out of water, although some are just a little bit less because they're fairly porous. Very heavy. And yet, with very careful observations, particularly the radar astrometry we can get, we can measure even 1 kilometer wide asteroids getting pushed around a few kilometers over a decade or so of observations. So we're seeing rubble piles the size of mountains getting shoved around just by sunlight shining on them in different ways. So that was kind of impressive. The last maybe 15 years, we've realized something else, which had been suggested theoretically, again, long before. And this is the Yarkovsky-O'Keefe-Radziwiecki-Paddock effect. We will call this YORP. So if we have an asteroid, if it's a perfect sphere, then this is Yarkovsky's model. But asteroids aren't spheres. You saw just how irregular they can be. Even if something's overall shape is spheroidal, it's going to have piles of blocks all over the surface, probably. So these irregularities mean that the net effect of this extra heat coming off can be offset from the asteroid's center of mass, so it can get a torque. So not only is it getting pushed, it's getting spun up or spun down. So how does this work? This is a binary asteroid called 1999 KW4. I apologize for the telephone numbers. With so many asteroids, it would be a pain to think of hundreds of thousands of names. But Steve Ostro, who is my thesis advisor at one of my thesis advisors at Caltech, observed this system quite some time ago now, and realized that KW4 has a couple of interesting properties. One, it has a satellite orbiting around it. We have a large asteroid and we have a small asteroid around it. And two, it has this big bulge around the equator. Where did that come from? Well, consider the York effect. We have a pile of rubble sitting in space. We keep spinning it up and up and up and up. Eventually, it's going to bulge out around the equator. The Earth bulges out by about 1 part in 300 because the Earth's gravity is quite large and the Earth isn't spinning that fast. We take a very small asteroid, we spin it every couple of hours, it's going to bulge out quite dramatically around the middle. Now, if it's a sphere, roughly speaking to begin with, if it was a pure fluid, it would act like the Earth. It would become an ellipsoid. But these are piles of rubble. The fact that they have compressive strength and internal friction starts to matter. And you end up just bulging out material around the equator and getting an actual ridge as opposed to a smooth ellipsoidal shape. You also can get various irregularities. KW4 is pretty much round around the middle, but there are other asteroids where we see large dents in those equatorial ridges. It's not clear if those are impact craters or if it's just we spun up this asteroid and bulged it out, and the arrangement of blocks in the inside happened to give it that shape. As it spins up and up and up and reconfigures itself, we have another complication. I talked about how York depends on the asteroid's shape. Shape just changed. Oops. Now all the York torques are different, and so there's this complicated sort of random process where asteroids spin up over tens of thousands or hundreds of thousands of years, reconfigure themselves, and then may either keep spinning up or spin down again. If they keep spinning up, eventually material at the equator goes into orbit. So the asteroid literally flies apart. This was the original suggestion for York, is the rotational bursting. The idea was that asteroids would spin up so fast that they would actually explode. That relied on the object having enough tensile strength that you could spin it up so quickly that when it broke, pieces were traveling so quickly that gravity couldn't hold them together. If it's a rubble pile, very loosely consolidated, you can sort of shed off material and form a moon and it will stay in orbit. And maybe 15% or so of asteroids a few hundred meters wide, the Earth objects anyway, have satellites like this. So that's pretty cool, I thought. So this is all very interesting and unusual physics, but what does this have to do with the Earth? This is where the danger part of the title comes in. It may seem a little bit overblown, but it could have been worse. Louis and Walter Alvarez, who used to be over at Berkeley many years ago, had a book they entitled T-Rex and the Crater of Doom. You can find it. Copies around. And they were referring to this. So this is the Yucatan Peninsula in southern Mexico. 65, 66 million years ago, an asteroid 5 to 10 kilometers wide hit the Earth. Right there. It made a very large hole. That hole is now actually not that obvious on the surface. It's covered up by the last several tens of millions of years of sediment. But if you do very detailed geologic mapping, it shows up. There's lots of fractures in the limestone rock, so if you are on the part that's currently on land, you find a huge number of sinkholes in the rock, tracing along the crater rim. If you look at the bedrock underneath all the sediment, you see this nice double ring pattern. So this is a very large crater, 66 million years old. Geologists back in the 1980s were, even before that, were going around the world trying to understand a pattern. you find rocks that are 66 million years old. There are many different sorts of dinosaur bones in them. Then there's a very narrow layer. And then above that, there are very few dinosaur bones. No dinosaurs other than birds. And a lot of other species disappear too. There was a mass extinction event. What triggered this? Well, that layer that I mentioned, the KT boundary, the Alvarez is, again, over at Berkeley back in the 80s, did some very careful geochemistry, and they realized that layer globally is loaded with iridium. Iridium is an interesting element. If you take the mixture of stuff that we make planets out of, you tend to get metal, nickel and iron mostly, rocks, silicate oxides, and then water and carbon compounds. The Earth is relatively low on the water and carbon and very high on the silicate rocks and the metal. The metal all sinks to the middle of the Earth. So there's a very large ball of nickel iron several thousand kilometers below our feet right now. That ball happens to contain almost all the iridium in the Earth. It mixes in with the nickel and iron very well. It doesn't mix in with rock well at all. So all this iridium that you're finding in the KT boundary layer had to come from somewhere. It probably didn't come from the core of the Earth. One place it can come from is an asteroid, because you have a differentiated asteroid. You break it apart. Yeah, you can have pieces that have a significant quantity of iridium in them. Or you have a non-differentiated asteroid that has a certain amount just to begin with. So they predicted that there should be a large impact crater somewhere in the world that caused a mass extinction 66 million years ago. Here it is. So this is the dinosaur killer. Now, impacts like this happen on the Earth very rarely, perhaps once per 100 million years. They don't necessarily cause a mass extinction. There have been a half a dozen different mass extinction events in the last few 100 million years. Only the one 66 million years ago is convincingly linked to an asteroid impact. And the geologists and paleontologists can discuss that with much more expertise than I can. But large impact events like this do happen, just very infrequently. Now, there are more small asteroids than large ones. Smaller impacts happen more often. How many people here in the audience have been to Meteor Crater in Arizona? Okay, quite a few of you. You all recognize this picture. So Meteor Crater is several hundred meters wide and pretty deep. This was made by an asteroid about 50 meters wide, so much, much, much smaller. It is quite well preserved because it landed in the middle of the desert in Arizona. And this whole area around it is the ejecta blanket. So this object came down pretty much straight vertically. It happens to have been made of nickel iron, which a couple % of asteroids are. Busted up cores of larger objects from the main asteroid belt. Hits the ground. And you can go around now with a metal detector if the owners of the site will let you do that. And you can pick up bits of that meteor. So like this happens on the Earth every few thousand years. This one is about 50,000 years old. I forget the exact age, but it's quite well preserved. Most of the time they happen in the ocean, and then even if they actually reach the bottom of the water, they get covered over by sediment fairly quickly. There's a bunch of other impact events of craters of different sizes scattered around the Earth. Many of you may have seen this still from a video. If not, you can go onto YouTube. Those of you who are already watching on YouTube, again, look things up while you're watching me, you will see all sorts of videos of a place called Chelyabinsk in Russia. It's a city of 1 million people, roughly. Just over 5 years ago, this happened, just around local sunrise. So the asteroid in this case was about 15 to 20 meters across, much smaller than even the meteor crater in Arizona impactor. This one came at a very shallow angle, and so rather than actually coming to the ground intact, it was stopped pretty high up in the sky. Now the asteroid has fallen through the Earth's gravitational field at this point, so it's picked up quite a lot of velocity in addition to the many kilometers per second it already had relative to the Earth's orbit around the Sun. All that kinetic energy has to go somewhere. It gets converted, in this case, to heat and light and sound. The fireball very briefly outshone the Sun. There were a couple of cases of meteor sunburn, which is not UV burns, it's just the sunlight not sunlight, the meteor fireball light getting focused a little bit, people were standing in awkward locations and actually get significant skin damage from that. More common problem. What do you all do when you see a bright flash of light in the sky? I'm hearing various responses here, and people in Chelyabinsk had many different reactions. A lot of people ducked. Other people went to the window. The shockwave travels at the speed of sound. 30 seconds to a couple of minutes later, depending on where in the town they were, shockwave hits the window. There were a lot of injuries from broken glass. There are also a lot of injuries afterwards, people stepping on the broken glass. About $30 million US in damage, 1,600 people were injured. Nobody died, but it was a pretty near thing. Something like the Chelyabinsk impactor happens somewhere in the world about once every 30 years. Most of the time over the middle of the ocean. Less of a problem. But we'd like to know about the next one that happens over a city before it happens. So how do we deal with this? There's a large number of survey programs that have been funded by particularly NASA for the last more than 20 years now, and also significant funding from other countries. You see here the three most prolific at the moment: the Catalina Sky Survey in Arizona, the Pan-STARRS project in Hawaii. The Wide Field Infrared Space Explorer was initially an astrophysics satellite. It's been repurposed for its extended mission solely to find and track near-Earth asteroids and characterize them. The goal here is find every possible near-Earth asteroid before it comes anywhere near the Earth, if we can. There's also a project called Atlas, which aims to find things, most things like the Chelyabinsk impactor, with a few days to a couple of weeks of notice. They still have a blind spot because we can't really observe directly near the sun. There's a proposal out of the Jet Propulsion Laboratory in Pasadena, led by Amy Mainzer, that would called NEOCAM, that would use technology derived from WISE to look right near the sun in the infrared from space, which you can't do from the ground. And that way you can find asteroids that are coming straight towards us from that direction. But the general goal here is find as many near-Earth asteroids as possible, predict their orbits out as far as we can. And currently we're discovering about 2,000 near-Earth asteroids a year. I say we, I'm not involved in these survey programs myself. There are many dozens of people involved in all of them. And I don't want to take credit for the work of other people. I do mostly characterization of asteroids that have already been discovered. So this project has gotten called Space Guard after an old Arthur C. Clarke novel, but it has done its job. Initially, the goal was to find all near-Earth asteroids larger than 1 kilometer in diameter, because something like that, no matter where it hits in the world, we're going to have a very serious problem. Fortunately, we are now tracking all of those objects. We know that we're finding almost all of them because the rate at which we discovered them went up very steeply in the 1990s as CCD cameras got better and telescope surveys started operations, and has now dropped way steeply down almost to nothing. So we're finding and tracking almost everything that's more than 1 kilometer across in the near-Earth population. Above a few kilometers in diameter, we're tracking everything because spacecraft that are orbiting the sun can see large asteroids even on the direct opposite side of the sun from the Earth. They can't see the sort of 1 kilometer size ones. There may be a couple that are just on the far side of the sun most of the time. We'll wait for them to move around. But we can say there won't be any impacts by anything bigger than 1 kilometer across onto the Earth in the next few hundred years. There is one object that called 1950 DA that has a slight chance of hitting the Earth in the year 2880. I cannot yet rule it out. It's been annoying me for the past 10 years. Fortunately, we've got plenty of time to figure that one out. We are now extending the survey program down to find and track stuff down to everything down to about 140 meters. Maybe we can push it down to 100 meters. For stuff like Chelyabinsk size, you don't get decades worth of advance notice. You may get a few days or a week, which is enough to tell everybody in the affected zone to stay away from the window. When we find the asteroids, we want to characterize them as best we can and track them as precisely as we can. This is stuff that I'm working on, particularly with groups of people at the Arecibo Observatory in Puerto Rico. You see it in the upper right. And then the Goldstone site in Southern California, which is part of NASA's Deep Space Network and run by a group at JPL for the radar program. In this case, we send out a radar signal, we code it in time, we can image the asteroid we're bouncing the radar beam off of, and this gives us pictures like you see here. They're not as detailed as the spacecraft images, but we can study a lot more objects. And you see here just a wide range of shapes. Some are lumpy spheroids, they're not entirely round, but then you've got rocks scattered everywhere. You've got things like Itokawa, two pieces sitting on each other. This one here, 1994 CC, is kind of fun. It may not be entirely obvious. There's a bright dot there and there, above and below the asteroid itself. That's two small satellites. This is a triple asteroid system. It has two moons orbiting it, not just one. So we're doing full science here in addition to making sure they aren't going to hit the Earth. We do tend to get a fair number of false alarms, because initially we can't predict the asteroid's orbit all that well. We measure its position on the sky, we measure how fast it's going. There's inherent uncertainty in that measurement. We run the orbit out in time, the uncertainty region where the asteroid could be in the future keeps growing. It may not necessarily grow linearly, but generally speaking, further in the future, the harder it is to predict where it's going to be. So in 2011, we had this particular case, asteroid 2011 AG5. It was discovered early in January of 2011, hence the telephone number. Initially, our predictions of the orbit are pretty uncertain. There's a long region where it could be. We didn't know its orbital period perfectly, effectively. So it spreads out along a line. That line happens to intersect where the Earth will be in 2040. So the Earth is there. There's this long streak, hundreds of thousands of kilometers long. We say at this point that there's one chance in 500 of it hitting the Earth. But this is just a way of quantifying our ignorance of where exactly it's going to be. The first thing we want to do is go get more data and refine our knowledge of where the object is. So a year later, 2012, got observed again. We now know that in 2040, 2011 AG5 will be over here. The Earth is here, so it'll be a couple times further away than the Moon is from Earth. No risk to anyone. And if we're still doing radar astronomy in 2040, we'll plan some cool pictures. Okay. What do we do if we find an impactor? The really small ones, much smaller than tellubits, we go meteor hunting. In this case, we is Peter Yaniskins at the SETI Institute. Peter is a professional meteor hunter. So he gets to go to the most unusual places in the world if he thinks he can find meteors there. He found some stuff up in Sutter's Mill a few years ago. You may have heard about that one. It was some of the old gold rush areas that had meteors dropping off on them. He also got to go to northern Sudan. In 2008, asteroid 2008 TC3 was discovered. 30 hours later, it flashed in the sky above the Sahara Desert. This caused a certain amount of anxiety for a little while, because a bright flash is an explosion in the sky above Sudan is anxiety for people. But all it did was drop a bunch of meteorites across this section of the desert. So Peter Yaniskins moved over to Verdun. What we These are kinetic impact deflection and gravity tractor deflection. Kinetic impact deflection is, in concept, fairly simple. You shove the asteroid out of the way. But how do you shove a mobile the size of a small mountain? You take a spacecraft that has to be fairly heavy, and you run it into the asteroid as fast as you possibly can. So if you have a spacecraft that is 100 million times less massive than the asteroid, and you are traveling at 10 kilometers per second, we'll shove the asteroid out of the way by a tenth of a millimeter per second. That may not seem like much, but if you add it up over tens of years, decades out, you can deflect an asteroid by 1,000 kilometers, especially if you time it such that you do it before, say, a close will fly by before it can hit the Earth, because then its orbit gets changed more dramatically. This has, however, one disadvantage, which is that it depends entirely on the target that you hit. You don't know exactly how a rubble pile is going to react to getting hit with a hammer, let alone a large impactor like this. So there's an inherent uncertainty. How do rubble pile asteroids react to getting hit at 10 kilometers per second? We've done impactor experiments before. The Deep Impact spacecraft flew into a comet to study the mechanical properties of comets. It didn't change the comet's orbit perceptibly. Well, comets and asteroids are two different classes of objects. So we like to test that, potentially, on an object that can't hit the Earth, move it onto an orbit where it also can't hit the Earth, to have some confidence that we could do this in real time if we had to. There's a strict rule here. We're not going to create an impact hazard when we are trying to address the impact hazard. There's also the gravity tractor deflection approach, which we'll talk about for a couple of minutes. This one sounds more like something out of Star Trek, but it does actually work in concept. We talk about how the asteroid has very weak gravity. It's very weak, but it's there. So if I have a spacecraft, you see in the artist's depiction here on the right-hand side, next to an asteroid, there is a very weak gravitational pull from the asteroid on the spacecraft, pulling it downwards. At the same time, again, due to this third law, equal opposite reaction, the asteroid is getting pulled towards the spacecraft. Again, this is very, very weak. We don't normally think of mountains getting pulled towards us just because we're standing next to them. But if you're in free fall microgravity around the sun, this can accumulate with time if you can find some way of adding momentum to the system. You can do this by taking your rocket exhaust and angling it so that it misses the asteroid. Now, rocket exhaust is going that way, and if you balance everything perfectly, the distance between the spacecraft and the asteroid remains constant, but the asteroid is getting very slowly pulled in this direction. This has a couple of advantages. One is that it's very, very well controlled. You can apply the deflection gradually. You can see how much you've done. You can apply more and more and more. Whereas with the kinetic impactor deflection, you only get one impact per spacecraft because they're destroyed on impact. The gravity tractor deflection also is independent of the internal structure of the asteroid. You pull the whole thing nearly uniformly. Very slowly pull it upwards. The downside is that it's very slow. So you might need 50 years to move an asteroid by 10,000 kilometers and change an Earth impact to a non-impacting one. But, in principle, this can work. You do, however, have a formation flying problem due to very persistent control where your spacecraft is, and you have to have rockets that can run continuously at a low level of thrust for a very long time. There are rocket engines, solar electric propulsion designs of various concepts that can run for several years at a time, not for quite so long, and not for the asteroid. So there have been proposals by NASA and other space agencies to test both of these asteroid deflection techniques. So far, only the kinetic impactor deflection project has actually been approved. The asteroid redirect mission was the NASA concept gravity tractor deflection demonstration. That was canceled a bit over a year ago. But the DART mission is going ahead. NASA mission 7 is to conjoint hyperdex. DART is double asteroid redirection test. This in turn is part of the asteroid impact and deflection test speed. Those are the mission names. But the concept here is that we'll take a spacecraft and run it into an asteroid and see what happens. Now, the DART project is being led by Cheryl Reed over at the Applied Physics Lab right now. The goal is to run into the satellite of a binary asteroid, because in this case, we have a relatively small asteroid, Didymos Beta, visual designation for the thing, that's in orbit around a larger asteroid. And if we hit the spacecraft into the asteroid, it can destroy it on impact, and it shoves both the orbit of these two objects together around the Sun slightly. More importantly, it causes a much larger change to the orbit of the Moon around the main asteroid. So we have redundancy in the design. We can't measure the deflection directly by monitoring spacecraft or radar ranging, and we can observe just the light, we call the light curve of the system, time when that satellite passes through the asteroid's shadow at particular times, very precisely, and measure even a very small deflection, independently of any instrumentation that might be following along with the spacecraft. So DART is going forward. You can get information at the web address there, and is to do this deflection of asteroid Didymos Beta in 2022 if the mission goes ahead. We'll see what happens. I'm just going to finish up by mentioning that there's a lot of other asteroid missions that have happened. I've talked about some of them already, but I didn't realize actually just how many there are until I put this slide together. Despite actually knowing about all the missions, it just struck me as how many there are and made the list. There have been 3 asteroid missions in the past to near-Earth objects. The first one was the Mir Shoemaker spacecraft, which landed on the asteroid Eros after mapping the whole place back in the 1990s through to the very early 2000s. 2005, the Hayabusa spacecraft got to the asteroid Pallas, the other side of Itokawa, which I've mentioned before. And then in 2012, the Chang'e 2 spacecraft flew by the asteroid Toutatis. Chang'e 2 is part of the Chinese Space Agency's lunar exploration program. It was initially orbiting the Moon. They played some fun orbital mechanics tricks to fly it out of Earth-Moon space and arrange it to pass very, very close to the asteroid Toutatis, less than 1 kilometer from the surface, actually, which is a little bit closer than they had intended. So I'm glad the radar predictions of where the asteroid was and how it was arranged in space were correct. If I was giving this talk a month from now, I might be showing you pictures from Hayabusa 2, which is currently on a final approach to the asteroid Ryugu. It's closer to the asteroid than we are to the Moon right now. Makoto Yoshikawa's team is doing very good work there, and you have a lot of data soon. But right now, it's just the dot on the spacecraft's cameras. The OSIRIS-REx spacecraft is on the going pathway to the asteroid Bennu, which we have radar observations of, so we can make a computer rendering of it. But we don't have actual pictures yet. Those will come in August of this year. Bennu has a series of potential Earth impacts between 2175 and about 2200. The impact probability you may see assessed as 1 in 3700 or so right now. Again, that's just a way of quantifying our uncertainty of where the asteroid will be. OSIRIS-REx will provide extraordinarily accurate measurements of where Bennu is in space and how fast it's moving, better than we can get from the ground. And we'll do that for several years until it leaves the asteroid and come back to the Earth. A few years. And that should help resolve the ambiguity in where Bennu will be at the end of the 2100s. Ideally, it'll rule out the impacts, or it may rule out some of them, and we'll see what happens. I talked about AIDA on DART. That will actually visit another asteroid, 2001 CB21. Just happens to be able to fly by it on its way to Didymos. And then there's other projects. NEA Scout is a small satellite project by Julie Castillo-Ruiz down at JPL. Destiny is another small satellite project by Tohoku Are, Japan. That's to go to the asteroid Phaethon. Phaethon is kind of fun. It gets very, very, very close to the Sun, closer to the Sun than Mercury. So it actually heats up to the point that not only do we have Yarkovsky radiation around, but the heat stress actually causes dust grains to crack and fly off the surface. So it causes a meteor shower on Earth every year. No hazard to the Earth anytime soon, but it does create a nice light show. And then there's a proposed Chinese asteroid mission that would go to a couple of other asteroids, including an asteroid called featured in discussions of the impact hazard because it very briefly was assessed as having a few percent chance of hitting the Earth in 2029.